Welcome back. In our last class, we have learned the basic concept of Boolean algebra, and we have also seen the basic laws of Boolean algebra. And as I promised, in today's class, we will be learning the advanced laws of Boolean algebra. In our last class, we have learned that digital system is defined by either by Boolean expression or truth table or state diagram. Now, if it is suppose Boolean expression, then we know that to implement the digital circuit, we should use minimum number of logic gates. That means the Boolean expression by which we will define that system, that should be simplified. And there are three methods of simplification of a Boolean expression: Boolean algebra or laws, K-map or Karnaugh map, and Quine-McCloskey method. And we have already seen that in case of Boolean algebra, the variables, they are called Boolean variables. There are two events like true or false, or yes or no, or on or off. There are two Boolean constants, either 0 or 1, and there are three Boolean functions, or, and not. And in Boolean algebra, there is no place of fractions, decimals, negative numbers, square roots, or cube roots. So let's start the class with other laws of Boolean algebra. In this class, we will learn all other laws in three ways. Some of the laws we will learn by using values, some of them by using circuit diagrams, and some of them we will simplify and we will learn those laws. So first we will learn the commutative law, and this commutative law we have already learned in school level mathematics. So a plus b, it will be equal to b plus a. Here plus is the or operation between these two Boolean variables a and b. Now a can have values 0 and 1, and b can also have values 0 and 1. As we know, these are the two Boolean constants in Boolean algebra. There could be four combinations: 0 0, 0 1, 1 0, and 1 1. So out of these four, suppose if we choose the second option where a is 0 and b is 1, then here what we will do, a plus b, so it will be 0 plus 1, that will be 1. And from the right hand side, what it is b plus a, so it will be 1 plus 0, and that will be also 1. So hence it is proved. From both the sides we are getting the same result, and that is 1. And now if we choose, say, the fourth operation, 1 and 1, so a plus b, that means what, it is 1 and then or operation with another 1, so we know that output will be 1 only. And then from the right hand side, it is b plus a, so value of b is 1, value of a is also 1, and then or operation between two ones, and then again the output will be 1. So again from both the sides we are getting the same value. So whatever values we are choosing here for both these variables a and b, this equation or commutative law will be always proved. Now this was the or operation between both these Boolean variables. Now we will verify the and operation between these Boolean variables. Now again, if we choose the second set of values, so a and b, so a is 0, so it will be 0, and value of b is 1, so 0 and 1, that means that value will be 0. And from the right hand side, it is b and a, so value of b is 1 and value of a is 0, so that value will be output of that and operation will be 0. Now if we choose the fourth set of values, if we can choose any set of values, so fourth one, now again a and b, so here and operation between two ones, both the values are 1, so it will be output will be 1. And from the right hand side, it is b and a, so it will be 1 and 1, so again the output of that operation will be 1. So again from both the sides we are getting the same result, same value. So this proves this equation or the AND operation of this commutative law. Next we will learn the associative law, and this time this associative law we will be learning by the help of logical circuits. So we are already familiar with associative law, and this associative law also we have already studied at school level. So what we are doing here, first we are performing OR operation between these two Boolean variables b and c, and then with that result we are again performing OR operation with another Boolean variable which is a, and whatever will be the final result, that will be equal to if we perform OR operation first between A and B, and then with that result if we perform OR operation between with that OR operation of A and B and then C. So this law now we will understand in a better way at the level of logic gates. So here we have two input OR gate. So the both the inputs we are choosing as A and B. So it will be what? It will be OR operation between A and B. This will be the output, and the output of the first OR gate we are taking as one of the inputs of the second OR gate. And now the second input of the second OR gate we are taking as the third Boolean variable, which is C. So what would it will be? It will be A plus B, that is one input of the second OR gate, and then plus C. So this will be the output of this whole circuit. This was the output of the right hand side of this equation. Now here if we choose inputs of the first OR gate as B and C, then the output of this OR gate will be B or C, I mean B plus C, and that is taken as the input, one of the inputs of the second OR gate. And the second input of the second OR gate if we choose as A, then what will be the output? It will be A plus B plus C, I mean the OR operation between A and the output of this OR operation between B and C. So these two outputs will be same, and this associative law we can also prove by taking real values of these variables A, B and C by taking any combination of those values. Now there is another law which is based on AND operation between A, B and C. Again we will understand by logic gates. So here we have one two input AND gate. Let's choose the inputs as B and C. So what will be the output of this AND gate? It will be B and C, and then that will be taken as one of the inputs of the second AND gate. And the second input of the second AND gate if we choose as A, then output of the whole circuit will be one input is A and the other input is the output of this AND operation between B and C, and then we are performing another AND operation. So this will be the output, and this is what we are getting from the left hand side of this equation. Then what we will do, we can also perform this way. At the first AND gate level we can choose inputs as A and B. So this will be output A and B, and then that will be taken as the input of the second AND gate, and the second input we will choose as C. So the output of the second AND gate will be A and B, and then with that and C. So this is how we can understand this associative law at the circuit level. And then we will see next the distributive law. In classical algebra we have already studied that multiplication is distributive over addition and subtraction. So in Boolean algebra multiplication will be replaced by AND operation, and addition will be replaced by OR operation. So here we can see, or we can say that AND operation is distributive over OR operation, and that we can implement or prove this way. So what we will do, first we will perform the OR operation between B and C, these two Boolean variables. So here the input will be B and C, and the output will be OR between B and C, and that will be taken as the input of this AND gate, and the other input will be taken as A. So this is AND operation, so A and the second input is the output of OR operation between B and C. So this is the result of the left hand side of this equation. Now to implement the right hand side of this law, what we need to do is we will perform AND operation between AB and AC separately, and then we will perform OR operation, and that's what it has been done here. So between these two terms the common input is A. So this input will be our A, and that has been distributed over both these AND gates. And here the second input of the first AND gate will be B, and second input of the second AND gate will be C. So what will be the output of the first AND gate? It will be A and B, and the output of the second AND gate is A and C. And now we are performing OR operation between these two outputs, and these two outputs have been taken as the inputs of the OR gate. So the output will be A and B, and the second input is A and C, and between them we are performing OR operations. So this is the output of this logical circuit, which is the right hand side of this equation or of this distributive law. Now we have another distributive law where addition is distributive over multiplication. Again, addition is equivalent to OR and multiplication is equivalent to AND operation in Boolean algebra. So that again can be proved at logical level or gate level. So what we will do is, first we will perform AND operation between B and C. So this will be B and C, the output, and then we are performing OR operation. So the second input will be A and we are performing OR operation. So it will be A plus and then B and C. Now this was the left hand side of this equation or of this law, and to implement the right hand side of this equation, what we will do is we will perform OR operation between A and B and A and C separately, and then we will perform AND operation. So A is the common Boolean variable here, common input, so this will be our A, this will be, that can be taken as B, and this can be taken as C. So when we are performing OR operation between A and B, so the output will be A or B, and here the output will be A and C. Now we are taking these two outputs as inputs of the AND gate, and so the output of this AND gate will be, one input is A or B, another input is A or C, and then we are performing AND operation. And this is what the right hand side of this expression or of this distributive law. Next we will see another distributive law where we have 4 Boolean variables and also that we will implement using circuit. So here first what we are doing is we are performing OR operation between A and B. So this will be the output, A plus B or A or B, and then we are taking two more Boolean variables C and D. So here the output will be C or D. Now we are taking these two outputs as inputs of the AND gate, and then we are performing AND operation definitely. So it will be A plus B is one input and C plus D is another input, and we are performing AND between them. So this is the left hand side of this expression or of this distributed law. Now we'll see the right hand side, we'll implement that. On the right hand side of this expression we have 4 terms, and in every term we are first performing AND, and then between all those outputs of AND operations we are performing OR operation. So let's proceed one by one. So between these two AND gates, what we are doing, we can take this way, that these are the outputs of these two AND gates, and here the A is the common input, so we can take this as our A. Now the next Boolean variables, let's take this as C, and so if this is C, then the output of this AND gate will be AC because we have the first term as AC. Now the second term we have in this expression AD on the right hand side. This was A, this was C, now this is A, and that means this has to be D. And where from D is coming? So from here. So that means this input will be D, and output of this AND gate will be AD then. And now this C is coming here, so this is C, and another output associated with C is BC. So this is C and this input will be B. That means definitely this Boolean variable will be B, and this will be B and C, and the output of the fourth AND gate will be, this will be our B, and this will be what? This is D. So this will be B and D. Now what we're doing, we are separately performing OR operation between these two inputs AC and AD, and separately between BC and BD. So here the output of this OR operation will be AC plus AD, and here the output of this OR operation will be BC plus BD. And now we are taking these two outputs as inputs of this OR gate, and then what will be the output? So this is one input and this is another input of this OR gate. So finally the output of this OR gate will be, it will be AC plus AD plus BC plus BD. This will be the output of this final OR gate, and that is what we have here on the right hand side of this distributed law. So this is how we can implement at gate level and we can understand clearly. Next, we will learn one important law, which is absorption law of Boolean algebra. This law reduces a complicated Boolean expression to a simpler one by absorbing like terms. Now, this absorption law can be of two types, or absorption law and absorption law. And both the types we will see one by one. So first we will deal with AND absorption law, where we can see here we have A plus AB. And what we can see here is this AB has been absorbed and finally we have only A. And this can be easily proved this way. Say A means we can say that this is the AND operation between A and 1, that will give us A only, and here we have A and B. So what we can do is, here we can see that A is the common input between these two AND operations. So A can be taken as common. So what is left inside this bracket is 1 plus B. And as per Boolean algebra, we know that 1 plus any Boolean variable, this results 1 only. So that means finally we will be getting A and 1, and that means that will be equal to A only. So this is how we can prove. Next we will see the AND absorption law, where we have this expression. First we are having the OR operation between A and B, and then with that we are performing AND operation with A. But A plus B, that has been absorbed, and finally we will be having A only. So this can be written as A and operation between these two variables, and plus or operation between A and B. And since we are here, we are performing AND between same Boolean variables, so we know that output will be A only. So it is A plus AB, and just now we have seen that A plus AB is nothing but A. So that means we can say this will be giving us the same result, which is A. Now we'll see another OR absorption law, which says that A plus A complement B, that is equal to A plus B. We can arrange this way: A, and then it is AND operation with 1, and next we have A complement and then B. This is AND operation between A and 1, and 1 can be written as 1 plus B because that results 1 only. And then here we have A complement B. So next we can write as A plus AB and then A complement B. We can write this way: A plus, between these two terms B is the common Boolean variable, then within bracket we will have A plus A complement. And as per Boolean algebra, we know that A plus A complement gives us 1, because if we take A as 0, then A complement will be 1, and if we take A as 1, then A complement will 0. Finally, if we perform OR operation, that will give us 1 only. So that means the output of this expression will be A plus B. Now again we have AND absorption law, where we can see that we are performing AND between A and another variable, which itself is the output of OR operation of one variable and complement of another variable. And very easily we can prove this. So A and here we have A complement or B. So what we can do is we can write this way: A and A complement and then OR A and B. And when we perform AND operation between one variable and its complement, that always gives us 0, that we know. So 0 plus AB, or A and B, and that gives us AB only. So this is very easy to prove. Next is another important law of Boolean algebra, that is consensus law, and this law simplifies a Boolean expression by removing redundant term. So let's take one example where we have AB plus A complement C plus BC, and what we are noticing here is this BC has been removed. Now in this type of consensus law of Boolean algebra, there are three conditions that are maintained. So the first condition is there must be three Boolean variables in that expression, and that's what we can see here: A, B and C. There are three variables. Each variable is repeated twice, and that's what we have noticed here. These three variables have been repeated either in the original form or in the complemented form. And the third condition is that the one of the variables will have its complement form in one of the terms. So here we are satisfying all those conditions, and then this third term is getting removed. as a redundant term. And here as the third term we have BC, so we can assume this way, that we are performing AND operation between BC, which itself is one variable, and then 1, and 1 can be written as, we will represent by the third variable, which is A with respect to BC, and A plus A complement means OR operation between one variable and its complement, that always gives us 1. So 1 can be replaced by A plus A complement. Here we can apply distributive law of Boolean algebra. So that will give us AB plus A complement C, and further we can write as BCA plus BCA complement, right? Now what we will do next is, we will rearrange all these terms. So we can write this way, AB first term, and then we will take the third term, which is ABC, and then we will take the second term, which is A complement C, and then in the fourth term also we have A complement. That's why we are combining second and fourth together, and first and third together. So here we will have A bar, then B, and then C. Now from the first two terms, what we can see is AB is common, so we will take common, and inside the bracket we will have 1 plus C, and then from the second and fourth, I mean from the third and fourth, here we will have A complement and C common, so what will left inside the bracket is 1 plus B. Now 1 plus B, now here from this first term we will have AB, and then 1 plus C will give us what? That will give us, as per Boolean algebra, 1, so it will be AB only. And then from this second term we will write A complement C, and again from this bracket 1 plus B is what? That is 1 only. So what will remain in the final expression is AB plus A complement C, and that's what we have on the right side of this consensus law. Now this has another law. In the first law, what we have seen was, first we performed AND operation, then we performed OR operation. And in the second law, first we are performing OR operation, and then we are performing AND operation. And here also the conditions that I said, those three conditions are getting satisfied. We have three variables A, B, and C. All those three variables are getting repeated twice, either in the original form or in the complemented form, and one of the variables has its complement. So the same variable we are taking A, considering A, and we are taking its complement. And now what we can see here is that B plus C, this term is getting removed from that expression as a redundant term, and this also can be easily proved. And here we have the third term, B plus C. So B plus C can be thought as B plus C plus 0, that is same as B plus C only. Now what we can do is, in place of 0 we can write A and A complement, because when we perform AND operation between one variable and its complement, we know as per Boolean algebra that result is always 0. So in place of 0 we are writing the third variable with respect to BC, we are replacing by that. Now this can be further written as, first term will remain as it is, A plus B, second term also A complement plus C, and this we will be writing as B plus C and then plus A, again distributive law, and then we will be having the AND operation, and again we will be writing B plus C and then OR operation with this A complement. Now what we will do is, we will take the first term and then we will take the second term, which is B plus C plus A. So we are rearranging the terms A plus B plus C, and now we are considering the third term, which is A complement plus C, and in the fourth term also we have this A complement. That's why again we are combining second and fourth. So the fourth term is A complement, and if we rearrange, then A complement plus B plus C. Now from these two terms what we can see is A plus B is common, so inside this bracket what will remain is 1 plus C, and from this two we are having A plus C common, so what will remain in this fourth bracket is 1 plus b. Now further if we simplify, then 1 plus c will give us 1 only. So what will remain is a plus b from these two terms, and again 1 plus b will give us 1 only. So from the next two terms, what will remain finally is a bar plus c, and that's what we have on the right hand side of this expression of the consensus law of Boolean algebra. So this class was all about the advanced laws of Boolean algebra. I hope this class was meaningful for you. With that hope, I end today's class. Stay tuned. Thank you.